So the Pythagoreans are also credited for the concept of figure-eight numbers, which they often would use pebbles and lay out regular discrete patterns in geometry, especially shapes like triangles, squares, um, and maybe regular hexagons. And they would use those to try to calculate different numbers and different concepts of numerical and geometric theorems. So it's that tie between an algebraic understanding with the geometric method. So here's one example of a figure number, the triangular numbers. And we have the first four figures in the sequence. And I want to figure out what's the fifth figure, the 10th figure, and how could I find the nth figure? So what I can do is I can start with the idea of looking at, I know that I have figure 1 has 1 dot, 2 has 3 dots, 3 has 6 dots, 4 has 10 dots. And if I look for a pattern, I can see that I'm increasing by 2, increasing by 3, increasing by 4. So I would assume that my next figure, the fifth figure, would increase by 5. So it would give me 15 dots. Well, how am I figuring it out recursively? So I could do that and continue to get to the 10th one, which is what I'd be doing if I was using the recursive pattern. And what the recursive pattern does is it says that the number of dots, f of n, is going to be equal to the previous number of dots, f of n minus 1, plus the current figure I'm on, n. So when I think about the fifth figure, the number of dots would be the fourth figure's number of dots, which is 10, plus the figure I'm on, which is 5. 10 plus 5 gives me 15. And this will work for recursive. However, the problem is that with the recursive formula, you always need to know the previous number to be able to find the next one in the pattern. And that can be a little tedious, especially if you're looking for higher values. So we also need to be able to find the explicit formula. So if I look at the pattern, I have the first 5 numbers in the sequence and the number of dots that they represent. Now, if this had been a sequence where it was just a n to the first as part of the explicit, these numbers, the differences between the two would be the same each time. Plus 4, plus 4, plus 4, plus 4, or plus 7, plus 7, plus 7, minus 8, minus 8, minus 8, minus 8. But they're not. They're continuing to increase, and that increase tells us that we have an exponent on our n value that is greater than 1. So we have to figure out, well, what is it? So we've gone one row, so we know it's greater than n to the first. Let's go another row and check out the differences. Going from 2 to 3 is 1. Going from 3 to 4 is 1. Going from 4 to 5 is 1. So that's the second row, which means that what I'm looking at is n squared, some explicit equation that has n squared in it. So I'm going to use the quadratic equation where we know that f of n is going to equal a, instead of x, let's make this a n squared plus bn plus c. Now we can figure all the parts out, and then we can go back and solve for a, b, and c. If I think about it, if I do sequence 1, I know that 1 was equal to a times 1 squared, because that was the first value in the sequence, b times 1 plus c. So 1 is equal to a plus b plus c. Now I can go to the second sequence, where I know that there is 3 dots, and I'm going to be looking at the second figure plus b times 2 plus c. So I know that 3 is equal to 4a plus 2b plus c. Now since I have 3 variables, I need to do a third equation. So I'm going to go to the third sequence. So 6 would equal to a. I'm in the third figure. So I'm plugging in 3 for each of my n values. So 6 would equal 9a plus 3b plus c. Now I have a system of equations that I can use to solve, and you can go through using any of the methods you want for systems of equations, and what you end up with is that your a value will equal 1/2. You'll end up with b value equaling 1/2, and then that leaves you with a c value equaling 0. So if I plug that in, I'll extend my page here, I'd end up with that f of n is going to equal 1/2 n squared plus 1/2 n, or you could write that as 1/2 n squared plus n.